So now we are starting the important chapter for GATE point of view, that is psychometrics. So now we will talk about psychrometrics. So in this chapter we will talk about the basic fundamentals of psychometrics. So let's start with psychometrics with the engineering definition. So I am now starting the psychrometry. So psychrometrics is nothing but the study of properties of air, water, vapor mixture. So we can write psychrometrics is the study of properties of study of properties of air, water, vapor mixture. Air, water, vapor mixture. Water, vapor mixtures. So now it's very clear in psychometrics we have to focus our attention on the properties of air, water, vapor mixtures. So now let's talk about atmospheric air. Atmospheric air. So atmospheric air is nothing but a combination of dry air and water vapor. So we can write atmospheric air. Atmospheric air is nothing but a combination of dry air and water vapor. So the dry air may be the combination of, or we can say that the mechanical mixture of various kinds of gases. It may be oxygen, nitrogen, carbon dioxide or some other gases. So for dry air we can define as dry air is a mechanical mixture of mixture of mixture of the gases, and in these gases there are oxygen, nitrogen, carbon dioxide, hydrogen, argon, neon, krypton, helium, ozone, and xenon. So this one is the mechanical mixture of gases. So if you see this mechanical mixture of gases, so major contribution is done by oxygen and nitrogen. So we can also write dry air is considered to consist of 21% oxygen and 79% nitrogen and 79% nitrogen by volume. Similarly, on the mass basis also we can write dry air is considered to consist of 23% oxygen, 23% oxygen and 77% nitrogen by mass. So now we can say that in dry air the major contribution is from oxygen and nitrogen. So now let's talk about the atmospheric pressure. So if P is atmospheric pressure and PA and PW are the partial pressure of dry air and water vapor respectively. Dry air and water vapor respectively. Then with the help of Dalton's law of partial pressure, then with the help of Dalton's law of partial pressure, I can write PA plus PW equals to P. Means the partial pressure of dry air plus partial pressure of water vapor will be equals to atmospheric pressure. Now again I am writing the Dalton's law of partial pressure, that is PA plus PW equals to P. So if you see this equation, in that equation P, that is atmospheric pressure, will remain constant, but PA and PW can change. So in reality the PW is very small. So I will write PW is very small. So the saturation temperature of water vapor at PW will be very less. So saturation temperature of water vapor at PW will be less. So how much it will be less? Will be less than atmospheric temperature. Will be less than atmospheric temperature. So right now just represent the atmospheric temperature by T ATM. So the water vapor in air is existing in superheated state. So water vapor in air existing superheated superheated state, and the air is called unsaturated air. Unsaturated air. So now it's very clear. We know the PW, that is partial pressure of water vapor, is very less. So the corresponding saturation temperature is very less compared to the atmospheric temperature. So that's why water vapor is existing in superheated stage. So that's why we are not able to see the water vapor in the atmospheric air by naked eyes, because it is in superheated state. And this air is called saturated air. So now I am drawing the TS diagram. With the help of this diagram, it will be very clear regarding this PW and atmospheric temperature. So now on y-axis just take T, and x-axis just take entropy, and I am drawing this down here. So now I am just drawing two pressure lines here. And second pressure line is lightened. So now I am marking the one point here, that is nothing but T atmosphere, the temperature at this point. So now suppose our air, that is atmospheric air, in that stage, it is step 1. So here the temperature is T atmosphere, and if we talk about in terms of PW, so PW will be this. So this pressure curve will represent the PW, and if you see the temperature corresponding to this PW is suppose T. So if you see the diagram, so T is less than T atmosphere, means the atmospheric air is in superheated stage. And now this air is called unsaturated air. Means unsaturated air means what? Here if we add more and more water, then the water vapor content of the air we can increase, but it will increase up to certain limit. So in air, if we add the water and the water content or water vapor of the air will increase, This kind of air is called unsaturated air. So suppose if we add water in atmospheric air which is unsaturated, then definitely the water vapor content will increase, and definitely the water vapor pressure will increase, and finally this pressure we can get PS. PS, that is the saturation pressure at atmospheric temperature. So at this stage the air will be saturated. So the maximum pressure we can get, that is PS. So now we are having two important pressure. One is PW. PW is the saturation pressure corresponding to the atmospheric temperature, and PS is the saturation PS, and here I can write this two pressure, that is PW is partial pressure of water vapor, partial pressure of water vapor at atmospheric temperature, and PS is saturation pressure, saturation pressure of pure water, of pure water at atmospheric temperature, at atmospheric temperature. So there are two pressures, one is PW and PS. Now we can define the ratio of this PW and PS by relative humidity. So now I am defining one term, that is relative humidity. So relative humidity, it is denoted by RH or sometimes phi, is defined as the ratio of, it is defined as the ratio of, water vapor as the ratio of partial pressure of water vapor PW to the saturation pressure, of pure water, that is PS, at same temperature of mixture, at same temperature of mixture. So now we can easily define these things. RH, or we can say that phi, is nothing but PW by PS, and in terms of mass also we can write mass of the vapor, and mass of the vapor at saturated state equals to, in terms of numbers of moles, NW by NS. So by this way we can easily define the RH, that is relative humidity. Already discussed that the atmospheric air is unsaturated air at atmospheric temperature, and it becomes saturated when the pressure, that is partial pressure of water vapor, will be the saturation pressure of pure water at atmospheric temperature. So by this way we can say that the relative humidity for saturated air will be 100%. So I am writing the important factor here. For saturated air, relative humidity, that is phi. For saturated air, the relative humidity will be 100%. So remember this thing, for saturated air, the relative humidity will be, and the specific humidity or humidity ratio. So now we will define specific humidity or humidity ratio. Humidity ratio, that is denoted by W. So it is defined as the mass of the water vapor per unit mass of dry air. So we can write it is defined as the mass of water vapor per unit mass of dry air in a mixture of air and water vapor. Air and water vapor. G equals to mass of dry air. If G equals to mass of dry air and small m equals to mass of water vapor, so we can easily define specific humidity, that is denoted by W equals to m by G. So specific humidity or humidity ratio is nothing but m by G. We are having one more formula for this W in terms of partial pressure of water vapor, that is 0.622 Pw divided by P minus Pw. So remember these two formulas, W equals to m by G and W equals to 0.622 Pw divided by P minus Pw, where Pw is partial pressure of water vapor and P is the atmospheric pressure. So now we will talk about maximum specific humidity. So I will write specific humidity will be maximum when air is saturated at temperature T. So for maximum humidity, I can denote by Wmax or I can denote by Ws. It will be equals to Ms by G, and Wmax we can also write in terms of pressure, that is Ws equals to 0.622 Ps divided by P minus Ps. So these two formulas are also important when we are interested in maximum specific humidity. Another important term, that is degree of saturation. Degree of saturation, that is denoted by mu. It is the ratio of actual specific humidity to the saturated specific humidity, or we can say that maximum specific humidity at the same temperature. So I will write it is the ratio of the actual specific humidity and the saturated specific humidity and the saturated specific humidity at the same temperature. So now we can write in terms of mathematical formula. Mu is nothing but W by Ws, and now I will give some of the important facts. Suppose if phi, that is Pw by Ps equals to 0, it means W will be 0, means the air will be dry air, and mu will be 0. Similarly, if I write phi, that is relative humidity is 100%, it means Pw equals to Ps, that is partial pressure of water vapor, will be equals to saturation pressure of pure water at the same temperature. Then W equals to Ws. Then specific humidity will be equals to saturated specific humidity, and in that case our degree of saturation will be 1. So remember, these two facts are very important, and sometimes they can directly ask in the GATE examination. So remember these 2 points. Find some of the important temperature in psychometry, that is dry bulb temperature, dry bulb temperature, wet bulb temperature, wet bulb temperature, and dew point temperature, and dew point temperature. So one by one we will define the dry bulb temperature, wet bulb temperature, and dew point temperature. So first of all I will talk about dry bulb temperature. So dry bulb temperature, it's nothing but a temperature recorded by a thermometer with a dry bulb. So it is a temperature recorded by the thermometer thermometer with a dry bulb with a dry bulb. So generally it is denoted by TdB. So the dry bulb temperature is nothing but temperature recorded by thermometer with a dry bulb. Similarly, wet bulb temperature, it is temperature recorded by the thermometer with but, thermometer with wet bulb with wet bulb. So it is the temperature recorded by a thermometer with wet bulb. So for making wet bulb, this bulb is enveloped by the cotton wick saturated with water. So means in thermometer there is a bulb. So on this bulb they are putting the cotton which is saturated with the water, and the temperature recorded by this thermometer is called wet bulb temperature. So now we have to discuss about dew point temperature. Now we'll discuss dew point temperature. So if a mixture of air and superheated water vapor is cooled at constant pressure, the partial pressure of each constituents remain constant until the water vapor reaches the saturated state. Further cooling causes condensation, so the temperature at which water vapor starts condensing is called dew point temperature. So I will write the definition of dew point. If a mixture of air and superheated water vapor heated water vapor is is cooled at constant pressure cooled at constant pressure, then the partial pressure then the partial pressure of each constituent of each constituent remains constant remains constant until the water vapor until the water vapor until the water vapor until the water vapor reaches the saturated state reaches the saturated state. Further cooling causes condensation. Further cooling causes condensation. So the temperature at which the temperature at which water vapor starts condensing water vapor starts condensing condensing is called dew point temperature. It's called dew point temperature. That is denoted by T dew point. So now we are having dry bulb, wet bulb and dew point temperature. So now I will discuss about adiabatic saturation process, and practically the adiabatic saturation temperature is equals to the wet bulb temperature. So for practical purpose, adiabatic saturation temperature we can take wet bulb temperature. So I am defining the adiabatic saturation process. So now I will define adiabatic saturation process. So now in adiabatic saturation process, I am just giving the brief idea what will happen. It's a insulated chamber that is partially filled with water, and here the unsaturated air is going into this chamber. Unsaturated air, and this one is insulated chamber, that is insulated chamber, and the air here that is unsaturated means in that case the humidity can be increased, means in that case the water vapor content can be increased. So when this unsaturated air is passing over this water which is in insulated chamber, then some of the water will evaporate and it will go along with the air. It means the specific humidity of the air will increase. So the energy required for this evaporation is given by this air. So what will happen? Equilibrium will reach when the energy given by air is equal to energy required for evaporation. At that time, the equilibrium will come. So now the unsaturated air will pass over this water, and the water water will vaporize, and this water vapor will go along with the air, and air at this end will be the saturated air. So this process we are calling adiabatic saturation process because we are getting saturated air adiabatically. So this one is the adiabatic saturation process. So now we will plot this process on TS diagram. Now let's plot the dry bulb, wet bulb and dew point temperature on TS diagram and the adiabatic saturation process also on the TS diagram. So I am just drawing the TS diagram here. So by this diagram all these things will be very clear. That is TS diagram. So I am just drawing the dome here. Now we know here that is one point and it's a constant pressure line. I am drawing here. Similarly, the other process I am drawing here with that. So now that is suppose state 1, it is atmospheric air. Atmospheric air. That is we are calling unsaturated air. So now from 1 that is a constant pressure, so it is cooling from 1 and it is reaching here. At that point the condensation will start. So according to the dew point temperature, if we cool the mixture of dry air and water vapor at constant pressure process, the point at which it start condensing is called dew point temperature. So this one is dew point temperature. Dew point temperature. So now here that is dew point temperature. Suppose this point is 2. So 2 is denoting the dew point temperature. According to our definition 1, it is dry bulb temperature. So we can say that 1 is nothing but dry bulb temperature and this 2 here it is nothing but dew point temperature. Dew point temperature. So now let's talk about this process. Suppose that is 1, 2, 3. So 1, 2, 3, what is happening here? This unsaturated air will become saturated adiabatically. So this one is adiabatic saturation process. Adiabatic saturation process. This one is adiabatic saturation process, and we have already discussed this adiabatic saturation temperature is also called wet bulb temperature. So practically we can assume this adiabatic saturation temperature is wet bulb temperature. So we can define that is wet bulb temperature. So by this way we can define dry bulb, wet bulb and dew point temperature on TS diagram. Talk about enthalpy of air water vapor mixture. So now we will talk enthalpy of air air water vapor mixture. So for this enthalpy I can write GH equals to GHA plus MHW. We know G is the mass of dry air, M is mass of water vapor. So here we can also write H equals to HA plus W by HW. So here we are having the formula for enthalpy of the mixture, that is HA plus WHW. So remember this thing, here H is enthalpy of mixture per kg of dry air, per kg of dry air. So remember this thing, here enthalpy is H is the enthalpy of mixture per kg of dry air, and the formula for that HA plus WHW. HW.